Well, here we are at the end of the class, and I just wanted to kind of recap some of the things we've seen before and take a view looking towards the future uh, in thinking about what to take from this class and ideas that will move you forward in future endeavors. So previously in the class, in this whole semester, you've learned a lot. You've learned a ton of things, and it's really quite amazing if you think back on it, how much stuff you've learned. You've learned how to represent and manipulate signals analytically and computationally. So, like at the beginning of the class, most people did not know what a signal is and what a system is, but now you've become very fluent in understanding signals, processing signals both computationally and analytically. You know how to represent systems. You understand what systems do and what kind of properties they have, like stability and causality. You've looked at transform techniques to understand how systems behave. That is, how do we describe the behavior of a system, what it does to input signals. And then you've seen transform techniques like Fourier transforms to understand the structure of signals. So we can understand that this signal is band limited and this signal is not band limited, and this is a high pass signal and a low pass signal, and we can understand how to manipulate the frequency properties of signals in order to get certain effects. So this two sets of transforms, one thinking about systems more and one thinking about signals more, really gives you a very flexible way of thinking about how signals and systems interact. And you've seen a lot of applications of signals and systems, such as audio and image processing, sort of multimedia processing, if you think about it, control system design. That first lab, we looked at object localization, and we have also communication systems. So these are the kind of natural follow-ons to the course, and so what I want to do is look towards what's sort of naturally comes next, and then also look towards some technologies where some of these ideas appear, and perhaps you wouldn't have thought they appear there, on first blush. So what is next? So all of the tools that we've learned so far let us analyze signals both on paper and in MATLAB. That dialogue that I talked about at the beginning of the class, that dialogue between the sort of computational and analytical, and this modeling of the real world, this three-way triangle between these three things let us start making the building blocks for more complex signals and more complex systems. Understanding these frequency-based, or what sometimes people call spectral methods, you'll see that term used before because we're thinking about the frequency spectrum. They give insight into many different problems in technologies that we interact with every day. So the natural follow-on courses for this course are digital signal processing, principles of communication systems, and introduction to automatic control theory. These are the signal processing, communications, and control are the kind of the natural follow-ons to linear systems. But actually these ideas that we've learned in this class carry on beyond engineering even, and to thinking about problems in science and economics and other areas, because you can often think of measurements as a signal, and then you can think about processing that signal using a system. So issues that we have not dealt with in this class are how to deal with noise in LTI systems. And so every system is going to have noise in it. So for example, in a communication system, you might have this modulator which takes a message M and maps it into a signal SM that you're going to send over a noisy channel, and that noise there, this noise gets added to the input signal. So how do we understand the properties of noise? How do we take simple LTI systems that we have looked at sort of in isolation, how do we put them together to build more complex functionality? And what sort of issues come up when we talk about implementation? Like there's the complexity of implementing something in a circuit, for example, or the number of adds and multiplies if you're thinking about doing something in discrete time or with a computer. And these kind of computational costs or implementation costs or hardware costs, all of this stuff we've put aside in this class to just understand like what is a system and what is a signal. But moving forward, these are the important things that you have to consider when you're doing design. And the last thing I'd say that we didn't cover that I think is important to think about is how do we model systems? Do we use physics to make a physical model of the system, or do we use data? That's the approach that people have been taking a lot in recent years, is to measure data and then try and estimate your system from that measured data, as opposed to using a physics model. So far we've been just given these signals and systems. We've given them to you as examples. So, and a lot of these models are based on physics, such as differential equations, and in physical systems, the frequency-based analysis, this Fourier transform story that we've been going through this class, that is a very natural way to think about stuff that comes out of physics, because you think about electromagnetic waves, there's frequencies right there, so that's like it's kind of the natural fit. But these new models that we encounter, new kind of data and new kind of signals that we encounter in more modern applications, are often just, we think of them as just data that we've collected, measurements that we've collected, and they may be related to some underlying physics of a problem, but they could be something else. It could be like a financial data or something like that. And so the question is, okay, well, do we then care about this frequency domain analysis? And the answer is, yeah, we still do, because these linear and LTI systems modeling can still be very effective and can yield a lot of understanding of what's going on in these types of signals as well. And then combining the ideas from this class with ideas in probability and statistics and probabilistic modeling and machine learning can be even better. So you see ideas from LSS appear in modern machine learning system in some things called like convolutional neural nets. As I said before, we haven't talked about noise, and real systems have to be robust to noise. So one question is, how do we model random noise signals? You've seen that before in a probability class. But we haven't really analyzed what's the impact of the noise on the LTI system, and how can we use LTI systems to, say, filter out noise or denoise. We saw an example of denoising earlier. And what are the new engineering parameters when we think about the design of these systems? And one important one is the signal-to-noise ratio, a term which you've probably heard before, SNR, signal-to-noise ratio. But the signal is exactly the type of signal that we've been talking about in this class, and the noise is the power of the noise. So we're looking at, when we talk about SNR, we're looking at the energy or power of a signal over the energy or power of noise. And that's this that's a measure of the system in terms of like what kind of, when you say what kind of SNR do I get, you're basically saying like how much is my signal getting swamped out by noise, or hopefully it's not getting swamped out by noise. LTI systems thinking lets us compose systems. So we stick two LTI systems together, we get another LTI system. One thing that we just sort of started touching on in this class is when he talked about Nyquist rate and sampling. That's how this interface between continuous time and discrete time systems. And so how do we understand how these two things compose? That's something that you'll see in the DSP class if you take it. How do properties like stability change when we combine different systems? So, I have a stable system and I put that input into another stable system. Of course, overall the system is going to be stable. But what if I have an unstable system and I wrap a system around it using feedback? How can I make the system stable? We saw examples of this from control, and there's more complicated ways of thinking about control systems. And finally, like what we're doing is there's a lot of connections between linear systems and linear algebra. In some sense, it's like a type of linear algebra that we've been doing. So can we build like an algebraic way of thinking about systems and how they compose and interact? So in this class, we focused on analyzing signals and systems, and in the future, you're going to be looking at designing systems. So this is a foundational class that lays the basis for you to be able to go and then design systems that have certain functionalities. So we want to understand what's the difference between a real world and an ideal system, how to design systems and build real world systems, that are not just in MATLAB, for example, that approximate like our ideal system. So we've seen a lot of ideal low pass filters, and we did a little bit of building Butterworth filters. But like, so how do we get close to building an ideal low pass filter? And what's the nature of the gap between the ideal and the real system that we can generate? We want to understand these engineering desiderata, like we want to have low energy, we want to have low delay, we want to have the system be stable, and there's a bunch of other performance specs. So these are the kind of, given that you need to hit certain targets, how do you design a system to meet those specifications? And how do you implement systems for computational efficiency? That is, I talked about this just a few minutes ago. We want to make sure that we're not doing something super inefficient, and we saw examples of that in the labs where simulating RF signal can be really complicated, and it can eat a lot of memory and can cause a lot of computational issues. And finally, if we're doing approximation, engineering is always taking approximations. And so what happens when you chain together multiple systems in this compositional way in a pipeline? What happens how do those approximations interact and build on each other? And do you get sort of a buildup of error or deviation from your ideal model? And how do you handle that in an actual design? So the follow-on to this class, as I said before, are communications control and signal processing. So let's take an example that maybe of signal processing that looks on the face of it to be a little bit outside the scope of this class, and that's looking at the human ear. So the cochlea in your ear is actually transforms sounds into neural impulses that are then transmitted to your brains. So if you get and the cochlea is lined with these hair cells which vibrate in response to the audio stimulus, and the damage to those hair cells can cause problems in generating the neural stimulus. So this is why people can get what are called cochlear implants to help with their hearing. What's going on in the cochlea is this thing called the basilar membrane, and that's the part of the ear that sort of translates the input signal into the audio signal that you get into the neural impulses. And it turns out that this is a series of bandpass filters. That the hair cells in the basilar membrane, or in the different parts of the membrane, respond to different frequencies, and essentially, so you get these high frequencies at the base, and at the apex you get low frequencies, and this response that you get out of the membrane is essentially a series of bandpass filters. That is a bunch of parallel bandpass filters. And so we can actually model that, and then we can design hearing implants that mimic the basilar membrane if it becomes damaged. So that's what we call cochlear implants. So you can see here that it's really just signal processing. We have an input source, and you have a filter bank. So a filter bank is just a series of parallel filters. And then you have a denoising operation, and then you translate this into a pulse generation, which is going to create different channels of output, which are going to stimulate the auditory nerves in order to translate the sound that is picked up by a microphone from outside the ear and actually directly stimulate your brain through the auditory nerve. So you can actually, in MATLAB, they have some stuff about cochlear implants, so you can sort of take a look at some of the MATLAB documentation to understand some of this a bit better if you're interested in this. So what does a cochlear filter bank look like? So you have a sound source, and you have a microphone which picks up this, measures, somebody's talking to you, measures, it's a microphone near the ear is going to actually take that signal, is going to pass it through a bunch of filter banks to simulate the cochlea, and then pass it through a translation from an analog signal into a digital signal, which can be used as the stimulus to your ear. And this is mimicking different parts of the cochlea. Over here, you see different parts of this filter bank, different branches of this filter bank, are simulating what the cochlea is doing, what the basilar membrane is doing at different locations, so at different frequencies. So another example that we touched on briefly in this class and via the labs is communication systems, but we talked about it as sort of AM radio, which is very, kind of simple way of looking at communication systems. But in reality, communication systems, you are essentially using signals to transmit information. And by information, I mean like bits, like zeros and ones. So instead of like taking an analog signal and modulating it, as we've seen before, we're actually trying to encode bits into signals. So the idea is, if you want to send a 0, you send a 1 signal S0, and if you want to send a 1, you send a signal S1. And if you want, and you can sort of generalize this to sending multiple bits at a time, and so on. And they'll have a lot of challenges, such as signal attenuation. There's noisy channels, there's synchronization issues, and there's all sorts of trade-offs for the engineering design in terms of energy, bandwidth, and rate, data rate, so bits per second, and the complexity of the communication system. The entire radio frequency spectrum is divided up by the FCC into all of these bands, and you can, if you get this this image, you can see like all the frequencies are being used essentially, sometimes by multiple parties. So some stuff is over for cell phones, some stuff is for military communications, some stuff is radio. Used to be there was a chunk for analog TV, and understanding the radio spectrum as a part of the electromagnetic spectrum is like a key element of trying to understand communication systems and how to design communication systems. So let's look at Wi-Fi. Wi-Fi is 802.11. I'm sure you're quite familiar. And in order for a device to be compliant with 802.11, it has to follow all of the protocols that are specified in the standard, the IEEE standard, the 802.11 standard. And this standard is very important. The standardization is really important for communication systems because it means things are interoperable. You can buy a Netgear router, you can buy a router from someone else, or Belkin or somebody else, and all these routers are going to be equivalent in terms of operation, in terms of the basic operations. They follow the same rules, and manufacturers have to make these standards compliant chipsets in order to go into these consumer technology. So let's look at 802.11 AC. In 802.11 AC, signals are transmitted in the 5 gigahertz band. In particular, this should be megahertz. So the total bandwidth is split into band limited channels with bandwidths of about 20 megahertz to 160 megahertz. And so if you want to see, if you want to look at Wi-Fi signals, you can get a Wi-Fi spectrum analyzer for your phone. There are lots of apps which will do this, which will kind of listen to what's going on and sort of show you what the frequency usage is. So basically, you've taken this big band of frequencies, you've chopped it into smaller band-limited chunks, and you're going to use those chunks to communicate stuff within each of those chunks. So Wi-Fi and all sorts of digital communication standards use digital modulation, which is different, a little bit different than our analog modulation for AM radio that we've seen before. And in digital modulation, you take up a symbol, which is like a collection of bits, like here in this picture is 4 bits, and you map it into a continuous time signal. And so one example of this that's often used is called quadrature amplitude modulation. And what it does is it maps bits into linear combinations of sines and cosines. So you can think of this as a signal diagram. On the x-axis, you have the in phase, or I channel, and so this A could be 1 or 3, for example. So 1 and 3. And then AQ is the quadrature, we call the quadrature component, and this can also say be 1, 3, minus 1, minus 3. And so we send a linear. We look at these AI and AQ. Those are two coefficients which I pull out of this signal diagram. It's called a signal constellation. And what you do is you send. Now here you can send you can send 4 bits over a chunk of this cosine. You send only t seconds of this combination of sines and cosines. So if you want to get higher data rates, 802.11 AC and also an LTE, 4G standard on your phone, it splits the channels that we had before, these channels, into even smaller bandwidth slices called subcarriers, and tries to send data in parallel. And the reason they want to do this is because the attenuation at different frequencies can be quite variable, and you want to be able to average out the kind of attenuation that you might get if you happen to get a bad subchannel. You don't want to be sort of be forced to live with a bad channel for the entire time. So this strategy is called orthogonal frequency division multiplexing, or OFDM, which is a term you might have heard before. And this is what an OFDM transmitter looks like. You take a message, you map it into the signal constellations to generate coefficients. There's a inverse FFT. You have digital analog converters, and then you have modulation onto a carrier frequency. That's like we saw in AM, and then it gets sent out over an antenna. So all the basic ideas in this thing are core to the topics we've talked about in LSS. Band-limited signals, modulation, and filtering at the decoder, which is not pictured in this diagram, but these are all ideas that we've seen in the class already, and it's just a matter of putting those ideas together and understanding the nature of the communication problem to really dig into understanding the communication system. So what happens at the decoder? So at the decoder, you might have you're sending one of these. You're sending a vector in this signal constellation. You're sending AIAQ, but what you receive is AIAQ plus noise. And so if I sort of map back to the signal constellation, what you're getting is like a sort of fuzzy ball around each signal point. If the signal points are far enough apart, that is AI and AQ have a wide spacing, then hopefully, and the whole noise is not too big, hopefully you can just take what you receive and kind of map it back to the bits that were transmitted. So the way this works in implementation is, you have a modulator which maps your bits to a signal. You add noise to it, and then you use something called a matched filter, which tries to detect the sine and the cosine. And then what you get at the output is sort of sampled output signal, and you use that to try and estimate what AI and what AQ were sent. And so this is called a hypothesis test, because you're kind of you have these different hypotheses about which message was sent, and you're trying to decide test was 000 sent or 0010 sent, and so on. And finally, we can talk about control systems. The Z-transform lets us understand how systems compose in terms of stability, and so does the Laplace transform. And lots of systems are unstable on their own, on the face of it. Hoverboards, airplanes, power plants, and a lot of robotics applications. So the whole field of control systems is basically how do you take these systems, wrap some feedback around it, and actually make them more stable. And so we can do this inverted pendulum example that we saw before. And if you haven't watched that video from MIT of Professor Oppenheim demoing the inverted pendulum, I highly recommend it. It's quite amazing. So we've seen already some of this before. We saw PID control. We did a little example of doing PID control. And here you have a plant which you want to control using feedback. We saw Black's formula, and we can do it. We did it for Laplace transforms. We can do it for Z transforms as well. And remember, the goal is to design the feedback system to stabilize G of Z. That is, when I look at the overall system, I want this thing to be stable, even if G is unstable. So thinking about systems in terms of block diagrams lets us try and use abstraction to design general tools for control. So um, we can think of these systems and composing these systems and use the fact that, for example, convolution is commutative, so that we can swap the orders of systems. We saw that before in proving the convolution theorem, and this lets us understand how to compose systems, multiple systems together, to build a overall control system from smaller components. And that's really critical to not getting lost in trying to design a very complicated system from scratch. You want to be able to reuse subcomponents in your design. One example in which feedback is very important is in robotics, and actually. Unimate was the first industrial robot. Was actually, we can have pride in New Jersey. Was the first industrial robot that was used in a General Motors assembly line in Ewing in 1961. And you can see a picture of this. There was an operator, but this robotic control arm actually, worked to put things together. It was really quite revolutionary at the time. And we fast forward to now, or like 5 years ago, you have 1.6 million industrial robots doing all sorts of things, working in warehouses, building all sorts of things, and doing a lot of jobs at high precision. Over and over and over again. In order to do that, you need to have good control systems that let you rely on the fact that the robot can do a repeated action and is going to remain controlled during the whole operation. So we saw before that microphones, or our ears, indeed convert audio signals into electrical signals. And so this brings up this issue that we talked about in terms of signal representation, is either how do we sample a signal and compress the resulting signal, and then how many bits of precision should we use, in this whole idea of data compression and storage of our signals, right? And sound itself is a signal. It's a time varying pressure wave. Then that pressure wave impacts your eardrums, gets translated by cochlea into neural signals, or it hits the membrane in a microphone and causes it to produce a voltage signal. One way to understand audio signals is through what's called the short time Fourier transform, or looking at the spectrogram of a signal. And spectrograms are used a lot in analyzing speech. So a lot of speech processing uses these Fourier transform techniques to understand what's going on in a speech signal. And you can tell different vowels will have different signatures in the spectrogram. And if you're a trained audiologist, you can actually sort of read a spectrogram often to figure out what's being said. It's really quite amazing. Other places where we see audio is auto-tune. And the early history of something like auto-tune is actually something called the vocoder, which was actually from 1928. And this was used to do speech synthesis, so we could have a sort of speech synthesizer. There's also something called the voder, which is even earlier, or maybe contemporaneously. That was like a speech generator. Also was used for encrypted communication. And basically, if you think about what auto-tune is doing, is it's like looking at the short-time Fourier transform and kind of mapping frequencies, instead of it's taking the input of where you want the frequencies to be, and then manipulating the STFT, the short-time Fourier transform. That's morally what's going on. So when you think about audio signal processing, you think about MP3s, for example, you're sampling at 44.1 kilohertz. And why do you do that? Why do we sample at 44.1 kilohertz? Well, it has to do with Nyquist, because the human hearing range goes up to about 20 kilohertz. And so the Nyquist rate is approximately twice that, 40 kilohertz. So that is, we have to include the positive and negative frequency. So 20,000 times 2 is 40,000. And so if you want to represent signals that humans can hear, you're going to use approximately this 44 kilohertz, or around 40 kilohertz. And so this is actually why the Nyquist rate explains why audio signals are sampled, at least music and so on, is sampled at that rate. We can also extend ideas of compression and sampling and signal representations to image processing. So here's an image of a castle. And what's used in to represent 2D signals like this is something called the discrete cosine transform. It's related to the Fourier transform. And we take a 2D version of this. So we take a 2D Fourier transform, or 2D cosine transform. And then what that does is it decomposes the image signal into frequencies along the horizontal and vertical directions. And we saw a little sample of that when we were doing edge detection before. But here we're actually doing a transform and not just a simple edge detector. And then the idea is that you've basically represented your image as a sum of these like 2D cosines, and then you want to reconstruct it using making it a linear combination of these 2D cosines. This is exactly how JPEG works. JPEG takes this discrete cosine transform of an image and compresses the components separately. And you can set the quality level of a JPEG when you make a JPEG. You can set the quality level, and the lower quality means you use fewer bits to represent each of the components, and that will lead to a blurrier image. So if I look at the difference between the original image and the JPEG compressed image, I get something that looks like this. So what you see is a lot of this fine detail has kind of been lost, and when you zoom in, you can see that this is I think this is zooming in on this window over here. You can see that some of the fine edge detail is kind of lost when you do the JPEG compression. You get sort of this patchy looking stuff there. And so hopefully that information is not important, at least from a perceptual standpoint. You look at the castle from the previous slide, and then you look at this one, and they look kind of the same. So in some sense, you haven't lost that much perceptually, but what you might have reduced the file size by a tremendous amount. So if we want to go beyond Fourier, we have these other ways of representing signals as a linear combination of some template signals, like we talked about dictionary learning. And so the idea is you want to choose the right template so that you can represent the signal with a very small number of coefficients here, and that will let you store the signal very efficiently. And this whole field of representation learning, or feature learning, is to design a good set of template signals based on data that observed signals that you have. So now that we've seen sort of what what we can understand in classes that follow on beyond LSS, let's expand the scope a little bit farther and see sort of beyond ECE style applications what kind of where do these ideas appear? Well, people use Fourier transforms to analyze financial time series. So, in one example, you have the Case-Shiller home price index. You can look at the frequency domain representation of that signal, and you can see spikes and try to interpret what's going on in the financial time series by understanding its spectral or frequency domain properties. People use LTI systems to model the operation in the brain of the neurons. They use, well, maybe not linear necessarily, sometimes nonlinear, combination of linear and nonlinear systems. And here you have if you want to look at a spiking neuron, that's what's called the integrate and fire model, where you have a signal that comes in some bias gets added, it gets integrated, and then once it passes a certain threshold, this is a threshold, then the neuron fires, a spike goes out on your neuron, and then when there's a spike that happens, it triggers, it resets the integrator. So people use these kind of ideas that we see and take a signal processing viewpoint in neuroscience quite often. So there's a lot of connections actually between neuroscience and linear systems, or systems theory in general. Another place where these two intersect is in medical imaging. So people trying to understand brain function and brain operation. Are you doing imaging, using CT or MRI to take a picture of the brain and then try and understand what's going on? Another application is in seismic monitoring. So, you want to, say, detect an earthquake or analyze the impact of an earthquake. And here again, you see the spectrogram appear. People are using the spectrogram, using the frequency domain properties of this time domain signal to understand the properties of the earthquake and try to get a sense of what's this vibration. It's a vibration, so you can see, because it's a vibration, it's operating at certain frequencies. And with this spectral analysis, this Fourier transform story that we've been going, is like kind of the right way to look at these sort of seismic signals. Finally, we talked about image processing, and sort of we think of sort of next to image processing is computer vision, trying to get a computer to understand images. And this is an old model, the AlexNet. It's a network which can represent images, sort of, and so you want to tell the difference between a cat and a dog, for example, and you can use this AlexNet to try and break apart and analyze the signal using combination of linear and nonlinear operations in order to process the image and do that detection. So modern machine learning uses deep networks all the time, more complicated models than AlexNet, and they often have these convolutional layers where you're filtering the image first, and then you're doing some post-processing, and then you filter again and you do some more post-processing. So computer vision actually relies on a lot of the ideas, a lot of the components in computer vision rely on ideas that we've encountered in this class. So in convolutional neural networks, you're taking a patch of the image, you're convolving it with a 2D, you're doing a 2D convolution, then maybe you subsample the overall image, and then you do more convolutions, and so on, and then you feed it into a regular neural network. And so you can think about this convolution as taking overlapping patches of this image, and doing some filtering on it. And this filtering is what's being fed in as kind of low-level features into this machine learning pipeline. And there's even more applications beyond these. Speech processing and speech recognition and machine translation, all of those rely on processing the speech signals. Speech is a recording, it's an audio signal, so you can understand a lot of properties of speech, as we saw from the spectrogram, using features that we extract out of the audio signal. The next generation of GPS, a lot of signals going on in GPS. How do you do that localization that we saw before? How do you design signals that allow you to do good localization? This relates also to radar systems and so on. Signals and systems thinking is also important when you talk about autonomous systems like drones and say networks of drones. You have like a flying configuration of drones. These kind of ideas that we see, basic ideas that we see in this class in terms of control systems, appear there as well, in terms of also looking at feedback control. And finally, there's a lot of work on what's called a smart grid. So there's both the control of the power system, but there's also communication that goes on within the power system, and how to design ways to use the power grid to do communication and do smarter control of power allocation and distribution is really, and been the last few years an emerging topic in engineering. So looking forward even more, you can think about the technologies that we see both now and going in the future. We have self-driving cars. We have Alexa, virtual assistants like Alexa or Siri. They're in the guts of them. They're doing a lot of signal processing, right? A lot of signal processing is going on there. We have the Mars rover and other sort of stellar exploration technologies. How do you communicate data back from something on Mars effectively? What's the best bit rate you can get? There's all sorts of and how do you control the motion of the robot on the surface of the planet? All this stuff is related to the kind of things that we've been looking at in this class. We're building the foundations to understand how those sorts of things work. And even in understanding, you can think of the genome as a signal, and so we can understand there's some work in genomic signal processing and also understanding the structure of genomic data, and there again you can use some ideas from this class or from the concepts that the conceptual approach that we take in this class to try and understand some problems there as well. So I hope this sort of gives you a sense of like all of the different ways in which this class kind of gives you a new way of looking at the world. And that's really the message I wanted you to take home from this class, is that there is this other way of looking at the world where things are, things that you encounter are systems that are processing signal. And anytime you interact with a piece of technology in particular, chances are it's using some sort of system to process some signal. And so the challenge to you is to identify what the system is and what the signal is for all these technologies, or what's one kind of signal that's going in, and what is the system doing to that signal. So signals are really everywhere, and systems are really everywhere. And we can think of your job as an engineer and designing pieces of technology as finding the right signals to measure and the right systems to process them. And so I hope that you get appreciation for this kind of way of thinking after this class, and I wish you all the luck in your future endeavors. Thank you very much.